we are going to introduce our work, UniRestore, Unified Perceptual and Task-Oriented Image Restoration Model, using Diffusion prior. Image restoration methods can generally be grouped into two key directions. First, Perceptual Image Restoration, or PIR, aims to improve image clarity and visual quality. These methods are effective at enhancing appearance, but they do not always improve performance in downstream tasks. On the other hand, Task-Oriented Image Restoration, or TIR, focus on optimizing images specifically for recognition tasks, such as classification or detection. However, they often produce results that are less visually appealing. This difference brings us to a key challenge. How can we unify both perceptual and task-oriented objectives in a single model without sacrificing either visual quality or functional performance? Diffusion models have shown remarkable ability to generate high-quality, detailed images. This motivates us to use the diffusion prior as the foundation of our unified restoration framework. However, these models are typically optimized for visual appeal and may not align with downstream task requirements. In this paper, we will introduce a unified image restoration model that adapts the diffusion prior by using task-specific prompts, enabling it to serve both perceptual and functional need. Specifically, UniRestore is built on a pre-trained diffusion model. We exploit the encoder features from its autoencoder as complementary elements to adapt the diffusion prior for different tasks. To achieve this, we introduce two core modules, the Complementary Feature Restoration Module, or CFRM, and the Task Feature Adapter, or TFA. The Complementary Feature Restoration Module is applied to the encoder to restore clean features from degraded inputs. These features are then fed through the diffusion process and refined by the decoder. The Task Feature Adapter works on the decoder side, combining the restored and generated features to generate task-specific outputs. Overall, our training pipeline consists of 3 stages. In the first stage of training, we focus on adapting the diffusion model to the image restoration task, specifically on restoring features from degraded inputs. We use a perceptual restoration dataset to train the Complementary Feature Restoration Module, the controller, and the SC tuner. The Complementary Feature Restoration Module is inserted into each encoder layer. It restores degraded features through 4 steps. In particular, intra and inter group convolutions are used not only to enhance contextual awareness, but also to model diverse types of degradation. Meanwhile, the controller and SC tuner are designed to guide the denoising process by injecting control signals into the UNet in a stable and efficient way. To supervise this process, we apply a layer-wise restoration loss and a control constraint, both of which minimize the difference between restored and clean latent features. Then the enhanced features and the generated features are passed as complementary inputs for the decoder in later stages. In the second stage, we optimize the Task Feature Adapter to adapt the diffusion prior to different downstream objectives while keeping other modules frozen to preserve the learn prior. The Task Feature Adapter is placed in the decoder, where it fuses the restored encoder features with diffusion features to produce task-specific outputs. Instead of building a separate adapter for each task, we introduce a lightweight, learnable prompt vector that controls how features are adapted at each decoder layer. This allows UniRestore to handle multiple tasks, such as perceptual restoration, classification, and segmentation, within a unified model guided only by task prompts. In addition, one key advantage of UniRestore is that it can be easily extended to new tasks. After the 2-stage training, we can support additional downstream tasks by simply introducing a new task-specific prompt. This stage doesn't require access to the original data or retraining the model. Only the new prompt needs to be optimized. This makes our approach flexible and highly scalable for real-world applications. To evaluate UniRestore, we conduct experiments across 3 tasks: perceptual image restoration, classification, and segmentation. The datasets used in our experiments can be grouped into 3 categories: seen datasets with synthetic degradation, unseen datasets with synthetic degradation, and unseen datasets with real-world degradation. We compare UniRestore with both PIR-based and TIR-based methods. For a fair comparison, each baseline is trained under its original objective and also under the UniRestore multitask setting when applicable. In the PIR task, traditional PIR-based methods are good at removing degradation patterns, and UniRestore not only reduces artifacts but also reconstructs finer details, resulting in better visual quality. For classification, the restored images emphasize high-frequency information, and activation maps demonstrates UniRestore's outputs align more closely with those from high-quality ground truth images. In segmentation task, UniRestore helps models generate more accurate object boundaries, demonstrating stronger spatial consistency in the results. Quantitative results show that PIR and TIR-based methods perform well on their respective tasks, but struggle when applied beyond their original objectives. In contrast, UniRestore achieves strong performance across perceptual restoration, classification, and segmentation using a single unified model. Our method outperforms existing baselines even in multitask settings and generalizes well to unseen datasets and unknown downstream models, demonstrating its robustness and scalability. We also demonstrate that UniRestore can be easily extended to object detection without retraining the model or affecting existing tasks. The ablation study shows that each proposed module can contribute significantly to the overall performance in both PIR and TIR tasks. Finally, visualizations confirm that task prompts effectively guide restoration toward different objectives, enabling flexible and efficient adaptation with minimal computational cost. Thank you for your attention. Please read our paper to find out more.